Okay, so we said before we would figure out why soap bubbles are colored. So imagine here the film of the soap bubble. So what is a soap bubble? It's just a thin layer of water with air inside. The water is a little bit soapy, but mostly it's just water. So we've drawn that, zoomed in here, so that we can see the thickness of the water better. It's very, very thin, but it's there. So now we imagine this light reflecting off of the surface, which is what we're seeing over in this image over here. There's a light up above, and it's reflecting off the surface, and somehow the film colors the light. So let's draw the light that comes down and bounces off the surface. Now, that's the light that bounces off the first surface. The thing is that the light also transmits into here and continues on its way. But part of the light gets reflected again from this surface and then comes out. So we see that to arrive in this region, there are two paths. There's the path that goes direct like that off the first surface, and then there's the path that comes down here and bounces off the second surface, and they combine together when they come out. So we're back to the same situation as we had before, the interference of two paths. Now we know the formula for that the intensity will be the sum of the intensities plus twice the root of the densities times the cosine of the phase difference. Okay, so the phase difference is the difference between these two paths. Now we're going to do the case where I've drawn the light coming in at a fairly large angle, but we're going to assume that it's fairly small. So then these two lengths are the same, so there's no phase difference there. This is the common to both paths, so there's no phase difference there. So what's different is this part here, and that's just part of the second path. So in the end, the phase difference should be 2 pi times the path difference over the wavelength. The path difference, in this case, if we use t for the thickness, is twice the thickness because it has to go through that layer of water twice. And that allows us to calculate our path difference and our phase difference. And of course, now we can see that this phase difference is directly proportional to the thickness of the water. And it's inversely proportional to the wavelength. So if we do the special, just try one of the special cases. Let's suppose that the phase difference is a multiple of pi. So either a maximum or a minimum. If L is even, it's a maximum. If L is odd, it's a minimum. So this would be like this, which we can solve various ways, but let's write it as t is L times lambda over 4. Okay, so when the thickness happens to be a multiple of a quarter of the wavelength, then we get minimums and maximums. So we see that this is actually selecting out different colors. And so what we're seeing up here in this image is that there's different thicknesses of the film. And depending on what the thickness is, that will pick out a different wavelength, which will be a maximum. Okay, so the thicknesses reflect different colors, sort of like a filter. There's two technical issues with this. The first is a problem in this formula that's important. Now you might notice up at the top of this bubble here, it looks completely black. In other words, there's nothing reflected. And that's where the bubble is very thin. I'll show you another example in just a second, but this one is, you can see it here already. If we look at what happens with our equation, when it's very thin, t goes to 0, the phase difference goes to 0, and then we get a maximum. Okay, so there's something not quite right. And it's easy to fix, and it's a physical phenomena that we haven't thought about yet. So we need to add it. Okay, so let's look at this other example. This is just another soap film, but it's a video of it. And gravity is slowly pulling the film this way. So it doesn't look like it, but that's downwards for this film. You can see the fluid collecting down here. And so then up at this top edge up here, you're starting to see that it's getting thinner and thinner. So this film is sort of wedge-shaped. It's fat down at this bottom end, and it's thin up at the top. And before this, you can see the bars building up. Those are regions of constant thickness. Okay, but now you can start to see up at the top, it's starting to get this, it's about to pop. Because it's getting very thin. Okay, but there's this region up at the top now. Oops. That was very thin and black. So I'll show you just that final image. So up here in the top, there's this region where there's no reflected light, even though there's still a bubble. Okay, it's just very thin. And then the bars of different reflections and darkness and the different colors as it gets thicker and thicker. So what do we miss in the analysis? It ends up that waves can be inverted when they are reflected. So if we did, for example, had an electric field that was going into the board here, going along with this, out of the board. When it bounces off the surface, it could be either out of the board or into the board. It ends up that in this case, where it's bouncing off of something with a greater index refraction, it gets inverted. Whereas in this case, it doesn't. Okay, so there's those two possible kinds of reflections. One gets inverted, the other doesn't. It can be a little more complicated if the angles get bigger, but we're going to stick to the case where it's one of these two simple cases. Okay, so, and an inversion is the same as going half a wavelength. So we can think of it as a phase difference, a shift in the phase of pi or 0. Okay, so if it's reflecting off of something with a greater index of refraction, then you pick up an additional pi phase difference. So now let's do the same analysis again of our film of water. Okay, so, and let's first label our reflections of whether they have a pi or a zero phase difference at that reflection. So the first reflection here is off of a low index bouncing off a high index, so that's the one that has a pi phase shift. The second one is the opposite. It has a zero phase shift. So now if we write out the two paths, the phase for the short one is just our path plus an extra pi phase shift. The phase for the second one doesn't have the extra phase shift. So know the difference in the phase so it's almost the same as what we had before, but now we've got an extra little pi here. Whether you add or subtract the pi, it doesn't matter, it's a half of a phase shift anyway. And so now let's finish the analysis. So now we say, okay, let's go back to those special cases. So if the phase shift is L pi, L being even or odd, L gives you maximums, L even gives you maximum, L odd gives you a minimum. So this will be 2 pi. So we could get rid of the pi's. Okay, so the role is switched actually. So now when the thickness goes to 0, we have L is minus 1, which is an odd number, which means you get a minimum. So this now corresponds to what we see up here in this orange region up here. Okay, there's no reflection. Okay, so we need to also consider that when we're calculating these thin films, that we have two kinds of reflections. One picks up a phase shift and the other doesn't. The other thing is that we need to use the correct wavelength. The wavelength of light changes when it goes into something that is an index of refraction other than 1. So in a vacuum, we have this fixed wavelength, but when it goes into a medium, the wavelength changes. And we can figure this out because the wavelength divided by the period gives us this velocity of the wave, which is the speed of light in a vacuum divided by the index of refraction. So that allows us to write the wavelength as the speed of light times the period of the wave divided by the index of refraction. Now in a vacuum we could do the same thing, except we don't need the index of refraction because the index of refraction is 1. Okay. Now if we take the ratio of these two equations, we get this guy. Now the thing is that the period doesn't change. If you think about it, it makes some sense. If you have a wave, if it goes into a different medium, it can't very well have a little more waves coming out the other end. In the end, it has to be the same number passing through every second, even though they might be going slower. Okay. So that means we could cross those out and the C's, and so we find this nice equation for the wavelength compared with the wavelength in a vacuum when you know the index of refraction. So So it's just that when we're calculating what the phase change is based on the path, what we're really doing is counting wavelengths. So in these equations, when you have the wavelength, you need to think, where did this path difference occur? Or I should go to a different one. Let's rewrite it. Okay, so the question is, where did this path difference occur? The wavelength that you use down here has to be the wavelength where that path difference occurred. It should be fairly obvious, but you have to remember to do it. Okay. There's one other interesting effect is that we didn't look at, I drew this before, we didn't look at this part of the light that came through. So some of the light is reflected. So you might ask yourself, what happens in this region here where the light is reflecting purple? What happens to the light that isn't reflected? Okay, is it just eaten up? Or does it go someplace else? So let's look at that thing again and follow those. So what we have now, okay, so I've got a little recording here. So what we have here is a sheet of glass with a thin film on it. When it reflects light, it's reflecting green. So that's the light on my ceiling. It's not a green light, it's actually white, but it reflects green. And now here I can block the light by putting a piece of cardboard in front of it. And then what we see is the light that's coming from the screen of the computer up through the glass. So this is transmitted through, not reflected. We see it's red, sort of, if you will, the opposite of green. If I take it away, again, you see the green reflected light, the red transmitted. So let's go ahead and follow those two paths. So we've done the reflected one, right? This is these two paths here for reflection. Okay, so we know how to calculate that. Yeah, this is a slightly different scenario though, because the thin film is this section here. There's air up above and there's glass down below. So we have a sheet of glass. Let's say this is glass. So there's 3 different indexes now. So we need to count, this is a good opportunity to count our reflections again. So think to yourself, in this reflection here, this first reflection, is it going to pick up a pi phase shift or not? Okay, so you have to look at these 2 indices. So the incident index is less than the reflecting index. So that's one that does pick up a pi phase shift. So we'll put a little pi there to remind us. Okay, so that's in the first path. The second path doesn't pick that up because it's going through. So that isn't affect this second path, but we do have a reflection here. And that's the same thing. It also picks up a pi phase shift. Okay, unlike it did with the soap film. Okay, so again, we have the n equals 1.3 here, and n equals 1.5. So again, it's something with a lower index reflecting off of something with a higher index. So both of those pick up a pi. Now, of course, since they both pick it up, when you subtract them, they cancel each other out. So in this case, our phase difference is just due to the path difference, because the difference due to the phase difference due to the reflections is 0. Okay, because they have the same pi phase shift. So this will just give us 2 pi times 2t over the wavelength. And where is the wavelength? Well, it's that the path difference happens in this green part. So that's the wavelength in 1.3. Now, okay, so we've got that. Now let's try the second set of paths, the ones that come through. So the first one is nice and simple. It just goes straight through. Transmitted, transmitted. There's no reflections, nothing. Okay, the next path comes down, shares that with the first path, has this little extra piece, and then continues. So the only part that's this part here and this part are the same as in the original. So the only part that is extra is this part, again, a 2t. So now we have our phase difference for this part. So this was the phase difference for reflection. This will be the phase difference for transmission. Okay, so we have this same part, 2 pi, path difference over the wavelength. Where is the path difference occurring? In the green section again. So this is also that 1.3. Now we have to consider the reflections. Okay, so we've already calculated, we already know what this first reflection is, that's pi. The second one now is up here. So what kind do we have now? So we have a high index reflecting off a low index. So that's the one that gets no inversion. So in this one, we're going to have another pi because there's a difference of pi between those two. The sum of those two and the other one which had none. Okay, so remember the transmitted one, the one that's going straight through, had no inversions at all. The reflected path has one inversion. So the net difference is like that. So now, the interesting thing now is that this is the phase difference that we had for the reflection plus pi. That means that if this is an even pi, then this is an odd pi, because we have to add another one. So if this one is 2 pi, this is 3 pi. So anytime this one, the reflection, is a maximum, the transmission is a minimum, and vice versa. If the transmission is an even pi, then this has to be an odd pi. And that's what we're seeing with the glass. The reflection is green. That means, by definition, that the transmission has to be very weak in transmitting green. And the reason that we see green with a light is because it's good at reflecting green, but it's bad at reflecting red. So it's a minimum for red and a maximum for green in reflection, and just the opposite for the transmission from below. So that makes these thin films are actually kind of nice. They're sort of like, they sort light. If it either reflects it or it transmits it, and it does that it's sorting it by color in essence. It reflects some and transmits the others.